Lesson 7 today, we're going to talk about covalent molecular compounds here. So lesson 7, forming molecular bonds. So yesterday we talked about ionic and how there's that transfer of electrons, right? Gaining, losing electrons, we wrote charges, we showed the electrons being filled up. So when you think covalent, you should think nonmetals. You should think sharing electrons, the definition of covalent bonding. Compounds in which the atoms are together called molecular compounds. All those terms go together. Molecular compounds, nonmetals, covalently bonded, sharing electrons, all. Very important that you know how to do those very well. Okay. We have some rules for drawing some polyatomic ions, and I gave them all to you. You don't have to copy anything down here today. I gave them all to you there, and for me it's on the next page as well. We're going to skip the rules for today, all right? Because, I don't know, we are. Say something funny to try to do whatever. We're just going to skip those for today. The rules are great. We'll talk about them. Rules are great, but we don't need to go through 4 steps every time we draw something out, especially for the ones we do today. Today they're going to be, hopefully you find as well, they're going to be fairly straightforward and fairly simple. Okay, so we're going to jump right into some examples here today. For example, C4, H2O, and CO2. So these are obviously molecular compounds, nonmetals, sharing, etc., etc. So like I said, let's jump right in here. The first one we have is CH4. Now, like yesterday, the first thing you should do is write down the formula. You would say, I already have the formula. Well, that's good. But if I ask you to draw carbon tetrahydride, you probably should first start with the formula. That's going to help you. That'll tell you how many of each atom you'll need, just like yesterday. So we're going to draw some Lewis diagrams. We're going to make a list of atoms. These are neutral atoms, and they will not have a charge today because they're molecular, they're neutral, they share. No giving and taking, yes? Very different. So C has 4 valence electrons, carbon. Each hydrogen has 1. Okay, and I need 4 of them apparently. So I kind of make a little list here. Now, in the steps, one of the rules is you should take the one that forms the most, or the one that has the most unpaired electrons and use it as the central atom. There's going to be another term that you hear that you need to know. Okay, listen closely. It's called bonding capacity is the term. The bonding capacity, you can write that down. The bonding capacity refers to how many unpaired electrons you have. How many unpaired electrons you have. Unpaired electrons, of course, are electrons by themselves. So when we look at carbon here, what is the bonding capacity of carbon? How many unpaired electrons are there? This is not a trick question. How many? Somebody. Huh? 4. Yeah. Bonding capacity of 4. Hydrogen. Each hydrogen has a bonding capacity of what? Once again, not a trick question. Yes, 1. Alright? The rules that we skipped over, one of them says, and we should always do this, you take the element, or the atom that has the most bonding capacity, and we use that for the middle, for the center of our structure. So we're going to take carbon and put it in the middle somewhere. Okay? It's going to be the middle structure, or the middle atom, I should say. It's going to be kind of what the other ones attach themselves to. and it's going to depend on the shape. So the middle atom quite often dictates what shape we're going to end up with. Okay, and when we talk about shape, we'll get to that eventually here as well. Hydrogens, each one has one electron. Hey, look, there's one electron. So I can put one there maybe, one there, and one there. Okay, so 4 hydrogens happen to go around those four unpaired electrons. They seem to match up quite nicely. Remember, we're dealing with nonmetals, so we are sharing electrons, and we represent sharing electrons, remember, by lines, right? So CH4 actually looks like that there. CH4, otherwise known as methane, something you guys will learn next year in chemistry. Okay? So that would be the structure, the diagram that you would want to draw for this particular one, CH4 methane carbon tetrahydride. Okay? Now, why do they hook up like so, or how do I know that that's what it looks like? Well, once again, following the rules like that we kind of skipped over, but carbon has to be the middle structure. Are you going to put H in the middle and try and join a bunch of carbons, try and join a carbon to it with a bunch of hydrogens around that H? Remember, H only can form one bond, so it's probably not going to be the middle one, right? Because once it bonds once, it's done. There's nothing else it can bond to, right? So we have to keep in mind kind of which ones form the most bonds. That's the one we want to put in the middle. Bonding path, the highest bonding path. Okay, I was going to mention one more thing. Why do they hook up like this? Because they want to become more stable, yes? We've talked about this before. They want to follow the octet rule still. They want to have 8 electrons around each element. Hydrogen still wants to have 2. So, here's hydrogen, there's hydrogen, there's hydrogen, there's hydrogen, and look, here's carbon. Okay? So you can see that carbon has 8 now. It had 4 before, but we're making this molecule. All these atoms come together, and they're sharing their electrons, sharing those valence electrons, and they have full outside shell. Just like, for example, H2, last day when we drew it. Why did 2 H's come together? Because they want to become more stable. They want to become more like helium. They want to share those electrons. They want to have a full outside shell. Why does F2 come like that? Once again, they want to have 8 around each one. How are they going to do that? They're going to help each other out. Same with this here, except now we're just doing different atoms. All right? So that's CH4. The next one here is, I know this one, water. H2O. Once again, you should start with neutral atoms, a list of them. Let's see, 1, 2, 3, 4, 5, 6, right? Every oxygen has 6. Too short. Hydrogen, 1 and 1. Okay. So, according to our definition of bonding capacity, which one has the most bonding capacity? How much does oxygen have? Bonding capacity of 2, yes? Each hydrogen has 1, yes? So which one goes in the middle, or which one should I start with? Probably oxygen, yes? So we're going to do this, oxygen. 1, 2, 3, 4, 5, 6. I'm going to put a hydrogen here, put a hydrogen here. Well, I guess maybe I jumped ahead a little bit, but I'm sure you get the idea. Okay, and same thing. Okay, those 2 electrons shared between them. So you're going to end up with this here. Alright? The oxygen's got 8, the hydrogen's got 2. 2, 2, 8. Yes? Okay? Now, I told you guys to draw oxygen like that, like kind of a one, remember? I said you should probably draw it like this, it's going to help you. Does that look like it's a straight line? Does that look like it's a linear molecule to you by looking at that? Is it a straight line all the way across? No, it's not. Okay? So if you draw it properly, if you draw oxygen, your center atom properly, okay, based on what I showed you at the beginning of the year, you'll see that this actually has a bend in it. In fact, that molecule is actually called bend. Okay? So that's kind of important to make sure that you understand that we can't just straighten stuff out, and we can't just make a line out of it, even though that's maybe what we want to do. Okay. When we get to the Lego on tomorrow or Wednesday, no, what's today? Tuesday, Wednesday or Thursday, you'll see that water doesn't have a choice. It has to go into that kind of structure there. All right. Remember, though, these are two-dimensional. When you actually do it in three-dimensional, you'll see a big difference in some cases. All right. So just kind of keep that in mind for next day here. All right. Next one, carbon dioxide, I think. CO2. Carbon. Oxygen. You're going to say, do I really have to draw all these out? And the answer is, eventually, maybe not. Okay. Should you draw them out today? Oh, why not? Give you a little practice. Once again, okay, carbon's got a bonding capacity of 4, oxygen's got a bonding capacity of 2. We want to put carbon in the middle. We want to put oxygens onto that. Or you want to put oxygen, you might say, well, I want to put one up here, for example. Go right ahead. I don't care. Some people say, I want to put one here. Go right ahead. But I'm going to tell you, okay, and once again, it's a little hard to show you this yet, because we're just starting out. Molecules tend to be symmetrical. They try to take positions as far apart as possible. Everything tries to kind of equal out for the most part. So if I'm going to put an oxygen on that side, I probably should put the other one over here. All things being. Now you can put it below if you want to. In the big scheme of things, you get the same thing. You do. Okay. As far as what the diagram is going to look like, okay, it may not match up to actually what it is. Right. So try to kind of spread it out, and it's going to take a little bit of time for this. So you're going to have to be patient. So you're saying, I don't know what you're talking about with the shape thing, and why can't I put it at the bottom? Well, you're going to have to be patient. Okay. I can't tell you that right now. You got to wait for that. Okay. So, once again, you look at this and you say, well, the first thing I have to do is if I'm going to make CO2, if I'm going to make that a molecule or a compound, I have to hook them together. Because if I don't hook them together, currently what do I have? Do I have CO2 right now? No, I got carbon and I got some oxygen atoms, yes? I haven't actually made a molecule or a compound out of this until I do this. Now, I've actually connected those together some way. Now I have a compound. However, it's not a good one because, look, there's electrons by themselves there. Is that going to equal out to an octet around each one? Probably not, because last time I checked, octet means 8. 8's an even number. When you've got one by itself, that's probably not a good idea. I could hook up these two though, maybe, because they're on different atoms. So I could join those two together. And there happens to be one right here and one right here. And you might say, well, that one's on top and that one's on the bottom. Are you sure I can do that? Well, remember, electrons are always moving, right? We are doing a two-dimensional diagram, fraction time. We're trying to represent it accurately. So we have to just keep in mind that all this stuff's moving, right? They're being shared. So can I do that? As long as they're on different atoms, sure. I'll tell you what you can't do though. If there's one here, for example this one, and there's one here, those two cannot hook up. It's too far away. They have to be between two atoms. Okay? That's too far away. There's an atom in between. So why wouldn't this one and this one hook up here, for example, these two here, right? Those are the two that will hook up to be shared. If you're going to go to the next step there, that's a little too far. All right? So, what do we get here? Well, we got this part here so far. Right? These two here can hook up. Another covalent bond. That one and that one can hook up right there. Okay? So that's carbon dioxide roughly looks like. I'm going to make a little. Basically, that's what it looks like. All right. So we end up with what, of course, remember, guys, the best diagram is this one here. Once again, you might say, what's the big deal? And I'm going to tell you right now, not much, okay? You give me that one right above that one, I'm okay. I'm good. I'm happy. That one's better. Why? Because it comes down to something we're going to talk about later, and I've said this before. Valence shell electron pair repulsions are your best. Pairs of electrons try to repel each other. They try to get as far apart as possible. When we do the model thing in the next few days, you'll see they take positions as far apart as possible from each other. Okay, they try to spread themselves out. Even these two bonds, they actually. All right, so just keep that in mind. All right. Let's see, that's CO2, and the next one was N2, which we've done before. So I'll just do that one real quick here. N2 is a molecular element, of course. N looks like this, right? And that triple covalent bond, we've done this one before. We did this in the molecular elements. I have no brighter, clever friends, people stupid, right? Make sure you know those, by the way. Right? Because these two can hook up, these two can hook up, and those two can hook up. So we end up with something, oops, sorry, that there, yes. And then, of course, one electrons possible from each other. So something like that. Symmetrical kind of things. If you can do symmetry, you're probably encouraged to do so for the most part. Okay? Try to get the same thing on both sides. Okay, good. That was N2, and then I think the next one you have is CHCl3. So let's do that one maybe. Was that okay? Do you have to go back? That one's in your notes already, right? No, N2 is. It was. One day it was. Yeah. Okay, good so far? Okay. Like I said, do you kind of see that these are pretty straightforward? They usually match up as long as you know how many valence electrons there are. And, you know, they kind of match up, right? So I don't think we need a bunch of rules for these quite yet. Then this one here, CH3 or CHCl3. Once again, carbon, right? Hydrogen and chlorine, chlorine and chlorine. All right, such as that. So carbon in the middle, bonding capacity of 4. You might say, okay, I want to put my hydrogen on next, or one of the chlorines. I really don't care. Where do you want to put the hydrogen? Top, left, right, bottom, top? You know what? It doesn't matter in this case. You can put it on the top if you want. You can put it on the bottom. You put it on the left. You know, somebody's going to buck the system. Somebody's going to put it on the bottom right, just to be different, right? That's okay. Into that thing where you're your own person, that's encouraged, I think. Anyway, if you want to put it on the bottom, I don't care. Okay, you just flip it over. It's the same thing. Remember also, these molecules turn, right? They turn this way. They turn upside down. They flip, etc., etc. So I don't care what you do in this particular case, as long as in some way, shape, or form, you don't try to make a new molecule. It's not possible. So once again, you can see they kind of match up quite nicely. Okay, you're going to be like, this is easy, good. If it is, if you're a little confused, we'll get you more practice here, I promise. These are very important to know how to draw. Will we do any more complex ones in this? Yes. Much more complex? No. Okay, but you have to be able to know how to do this to do basically the second half of this unit. Okay, so there's an example. If you want to put the H on the bottom, that's fine. Flip this one over, you get the same thing, right? Or turn it 90 degrees, and you should be fine. Okay? What's the next one there? I forget. I guess I could just look here because you're not going to tell me. Oh, that one. We're going to skip that one. We're going to go to C2H2 now. C2H2. C2H2, same thing. You want to start with, you know, writing out the list here. And then we got an H and an H. Now you might say, well, which atom do I put in the middle here? Which one's the middle one? And the answer is, well, not hydrogen, probably. Carbon's got 4, so we probably should start with one of those. Which one? Up to you. I don't really care. Technically, this one really doesn't have a middle one. It's got two middle ones. Okay, so C2H2. So we're going to start with both of those there. Yep. Yep, it is. And then, of course, okay, we got that labeled. We need two hydrogens. And once again, it ultimately doesn't matter where you put them. You can put them both on the top if you want. You can put them both on the bottom. You could put one on the top and one on the bottom. You could put one on the left and the right. That's the one I like, and that's the one I'll do, because I like to keep things symmetrical if possible. So I'm going to put one here and one here. I'll tell you what you can't do, though. Not a good idea, is to put both hydrogens on the same carbon. Because if you do that, if you put both hydrogens on the same carbon, then you're going to end up with not able to basically work out the rest of the electrons. They're not going to match up. Okay, and you're going to run into problems. And I'll show you what I mean when we do the next one. Okay, so they're not all just easy peasy pretty ones. Once again, to make a molecule, I need to hook this all together. So that's probably my first step there. And then you look, hey, look, there's two unpaired electrons on the bottom. Maybe those two could match up. You might say, once again, if you're you want to do your own thing, you might say this bottom one and this top one up here want to match up. Okay, whatever, right? But these two here can match up, and those two there can match up and create other covalent bonds. So you end up with something like that, okay? And you'll learn how to name that in grade 12, okay? So there you go. Once again, you should always check to make sure hydrogen's got 2, hydrogen's got 2, carbon's got 8, carbon's got, oops, 8, okay? So always double check to make sure that's the case, because if that's not the case, then it's not right. I can pretty much guarantee you. Just save yourself some time and mark your own kind of thing, you know what I mean? Okay? Now, we missed one, so let's do that one here. It's HCOOH, yes, I believe? That one. So, before you guys start doing you'll have lots of time for homework, so don't worry about that. This one here, okay? They're not always going to match up nicely. You might say the first question for you might be, why is it called HCOOH? Is it because I just wanted to say OO? No. But I do like saying that because it's a little bit funny. Right, Liam? Yeah. HCOOH. No, it's not. There's a reason why. You might say, and if you don't understand what I'm just said, I am basically saying, why don't we just call it H2CO2 for crying out loud? Just get all the H's together and all the O's together. Why we got to label it all out? And the answer is, does anybody know why we write it all out? Aiden. It's not hydroxide because in this case, it is they're all molecular. So we can't use the charge OH minus for this one. What do you think? Cool? Oh, okay. Anybody else? Yeah. That's how you lay it out in the diagram usually, okay? However, you still need to know roughly, okay, how to lay it out properly. Because when you look at this, you say, I'm going to skip ahead. Now listen, the reason we wrote it out as OO, because I'm going to do an OO right here. Don't copy this down because this is wrong, okay? So what happens is, yes, usually it's written out like this because that's the way it appears. So you say, oh, okay, I can do this. I can follow that. So here's my C, right? Here's my H here. Good so far. Here's my O. I told you to draw them like that. This is wrong, don't forget. Don't do this. Well, you can, but you're going to have to cross it out. Then I'm saying, okay, my other O is attached to that O, so I'm going to put this here. I'm going to turn it a little bit so I can kind of match it up. Because remember, oh, speaking of which, what are these two here called? What are those called from you the other day? I'm going to pick somebody else. Somebody else. What are those called? I'll accept two names. Lone pairs are a good answer. Those are called lone pairs. And lone pairs rarely form bonds. Okay? So I don't want to put those, I don't want to put these two lone pairs here. I don't want to put them there because they're not going to form up with that electron, right? It's the unpaired ones. Another term that's also equivalent to lone pairs is called basically paired electrons, right? Same kind of deal, right? Paired electrons we usually use for just the atom, lone pairs for molecules, but all right. So good so far. And then I say, oh, there's an H there. I'm going to put an H here. So I'm going to hook this together. By the way, can molecules do this? Can they kind of go like that? Or am I just kind of out to lunch here? Do they have to go straight across, or they have to be kind of nice? Oh, there's lots of different shapes. Lots. Okay? So this is a possibility. Could happen. It's not with this one, but it could happen. Okay? So it doesn't have to be all nice and pretty and go in a straight line. Okay? What's my problem now? Is this good? I already told you it's not. You were listening, right? Yeah. But the other problem is it's not so much that I have two unpaired. Where are they though? They're on the same atom, right? So if this ever happens to you, this is not a good scenario. There's no way to fix this, because how are you going to get, you can't put a bond on an atom, right? They're both, those two unpaired electrons are on the same atom. So I can't hook this up with another one somewhere else because they're on the same atom. So, you know, you can do your octet rule if you want, but it's not going to work out very well here, obviously. So this is why we say pencils have erasers, pens have erasers, whiteout. Smartboards have erasers. Computers have a backspace key. Okay? So that's not good. So here's what I do know. Carbon. That didn't work out, so you just say, oh, well, it didn't work out. I'll try it again. Something not quite right here. I'll start with that, probably. I'm still going to put my O there. Okay? So I'm going to put my O here, but I think kind of where I ran into some problems was I put the other O on that O. I don't want to do that again, so I'm going to put the O maybe up here. Now, does that kind of follow the same thing that you see up there? Well, kind of, a little bit, right? H, C, O, and my other O is up here, and I could maybe put on an H there. How do I know to put the H on there? Well, I'm guessing, okay? I got to match them up. Why didn't I put the H down here? Maybe I could have. Who knows? Maybe you can do that and see if it works out to be the same thing. Never know. Okay? Hooking these up here, let's see. Got to make a molecule first, right? So I got to hook those up. Now, yes, I still have unpaired electrons, but is this better now? Can I do something with those unpaired electrons? Sure, you can make another bond there, right? So I'm going to take these two and match them up here. And I'm going to throw those into there. Okay? The important part is, right, how do you know if you did this right? It's easy. It's just like math, right? Once you find X, you plug it back in and see if it works out. Yes? Once you find this molecule, does each one have 8? Does hydrogen have 2? Well, I'm sure it does, but let's double check. 2, 8, 8, 8, 2. So it looks good. You give me that, I don't have a choice really. I got to mark that right because it follows the octet rule. So is that a possibility? Absolutely it is. Okay? Some of you might have put the H down here. Well, guess what? The double bond would go up here, and actually you get the exact same structure. Okay? And if you don't understand that, that's okay. But what I'm saying is you got to find out some way to make these match. So they're not all going to be straightforward and easy. Some will require erasers. That's fine. A little bit of challenging. It's good. Challenging is good. All right? So, questions, anyone? Sometimes, and there might be different structures with the same elements sometimes. So, for example, when you get to Chem 30 in Unit 3, one of the first things we have you do in that unit is find all what we call the isomers of this compound, this formula, C7H16. there's like 6 or 7 different isomers, structures of the same compound. Okay, they all have the same formula. So you might say, well, how are you going to grade these? Well, I'm going to look to make sure you have an octet, right? Are you going to get something that complex? No. But do you have all the carbons there? Do you have all the hydrogens? Do you have the oxygen? Do they fit that rule, right? Octet rule, and hydrogen needs 2. That's what I'm going to be looking for. And everybody in this class may not. That's not going to happen. But you might have 2 or 3 different structures as possible answers, and that's okay. I don't care. All right. The only other thing I have to tell you is that good? Any questions? Yeah. Okay. Yeah, you know what? That's good that you brought that up. The answer is no. But, good try. I always get somebody that wants to do this, that may try and do this, and kind of connect it like that, or I don't know how you did it exactly. But I get students that want to connect, make a ring, basically, we call that, out of those kinds of elements. And the answer is no. Can't do it. However, you might follow the octet rule, good point, but it won't happen with those. You can make rings though, having said that, but they all have to be carbon-based. So if you gave me this, I would have to mark it right if it was a different formula. So that is an option if you got a bunch of carbons. Let's not do that though. Let's save that for next year. Okay? But that is a possibility if you have all carbons. If it's carbons and oxygens, no. Okay? They won't arrange themselves that way. All right? So, no rings. How's that? Good point. All right, what else? Any other questions? Okay. Just a quick reminder as well. All the way over here. So I'm going to give you some, I don't know, what is there, 8-ish questions or so, 10. Oh, 11. Okay, 11, I lied. We're not going to get to the second half, so when you see there's another sheet of homework there, don't do those. Okay, I haven't shown you how to do those. Those are different. Those we need the rules for. We'll do that tomorrow. When you're doing your 11 questions for homework today, remember fluorine, chlorine, bromine, iodine are all in the same group, yes? Known as the halogens. And let's not forget, they all have 7 valence electrons, yes? So let's make sure we use 7 there. There's no such thing as 17 and all this other stuff. They all have 7. Oxygen, sulfur, you might get down to selenium. What if I got to do a selenium one? Same thing. They all have 6. They're all in the same group. Yes? Are you listening? You're going to get an arsenic one. What does arsenic look like? It looks like phosphorus and nitrogen. Nitrogen's got 5. Phosphorus has 5. Arsenic has, it's not your question, 5. Yes? They all look the same because they're in the same group, people. Okay? Carbon and silicon, of course, are pretty straightforward. They have 4, obviously. Okay? But they're in the group because that's why they're in the group. Okay? So just keep that in mind. And remember, we talked about carbon before. We said, hey, with carbon, it's got 4. Does it want to lose 4, gain 4? And I said probably not either one of those because it's really good at molecular compounds. Can form lots of carbon-hydrogen bonds. Very good at hydrocarbons, gasoline, things like that. Okay, ethanol and all that other stuff. Long chains of carbons too. Lots of carbons hook up together. That's organic chemistry. That's Unit 3 and 30 stuff. You'll learn. And then you can put oxygens on there and stuff like that and get a slightly different name. But long carbon chains, very good. Okay, they're good at sharing stuff. All right. All right, good.